Tonight, we're beginning with a question that sounds simple at first, and then becomes much larger the longer you sit with it. If a spacecraft left Earth in 2026 and kept moving outward, how long would it really take to get beyond the Milky Way? By the end of tonight, you will understand why the answer becomes so enormous so quickly, why a galaxy is not the kind of thing you simply travel across the way. You might cross a country or even a solar system, and why escaping it means stepping into a scale that pushes far beyond ordinary human thinking. And if space questions like this are the kind that pull you in, feel free to subscribe, because that's exactly what we explore here. At first, the idea feels almost clean. You leave Earth, point away from the crowded inner regions of the galaxy, and keep going until home is behind you. That picture makes sense for a few seconds. But the moment we try to attach a real speed to that journey, the size of the problem starts to show itself. One of the fastest spacecraft human beings have ever sent into deep space is Voyager 1. It is moving at about 17 kilometers per second relative to the Sun. That is an astonishing speed by human standards. It is fast enough to cross huge distances in the solar system, fast enough to leave the planets far behind, and fast enough to feel almost unreal when compared with anything we build for life on Earth. But inside the Milky Way, that speed begins to shrink. Our galaxy is not a small neighborhood of stars. It is a vast system, tens of thousands of light years wide, from where we are to anything that might begin to feel like the outside. And a light year is already almost too large to picture comfortably. It is about 9.46 trillion kilometers. Once distances begin stacking in the tens of thousands of light years, the mind naturally starts to lose its grip. So it helps to say the answer plainly, early. If we left in 2026 using the kind of speed human beings can actually achieve today, escaping the Milky Way would take hundreds of millions of years. That is the first anchor. Not centuries, not a few thousand years, hundreds of millions. That means the journey belongs to a span of time so large that normal travel language starts to sound misplaced. This would not feel like a voyage in the usual sense. It would feel more like deep history. If a spacecraft had begun such a trip when dinosaurs were still alive on Earth, it still would not be finished today. Continents would shift. Species would appear and vanish. Oceans would change. Entire chapters of Earth's story would come and go while the ship kept moving through the dark. And what makes this even more striking is that this first answer is still only a rough one. Because so far, we have treated the problem in the simplest possible way. We have imagined the Milky Way as a distance to cross, as though escaping it only means choosing a direction and moving far enough outward. That gives us a real starting point, and it is useful because it lets us feel the scale almost immediately. But the galaxy is more than a distance problem. The Milky Way is a physical system with structure, mass, motion, and gravity. We are already inside that system, moving with it. Our Sun is orbiting through the galaxy right now, carrying Earth and every human life along with it. So leaving the Milky Way is not like walking out of a room or sailing off the edge of a map. It means trying to get beyond something vast that has been holding us the entire time. That is why the number grows so large so fast. Even before we carefully define what counts as outside, even before we ask where the galaxy truly ends, even before we deal with gravity in any serious way, the journey is already operating on a timescale that barely fits inside human imagination. And that is what makes the question so worth exploring. Because once we know the first answer, the deeper mystery begins to open. What exactly are we trying to leave behind when we say the Milky Way? That is the point where the number begins to change shape. At first, hundreds of millions of years can sound like the kind of phrase people use when they simply mean very, very long. It can pass through the mind as a dramatic number without fully settling anywhere. But once we give it something to rest against, something human, it starts to feel different. Recorded human history reaches back only a few thousand years. The pyramids of Egypt are old by our standards. Ancient Rome feels distant. The earliest cities feel like the deep past. Entire religions, empires, languages, and ways of life have risen and fallen inside a span that is tiny, compared with the travel time we are talking about here. If a spacecraft left Earth and needed hundreds of millions of years to finish its journey, then all of recorded history would fit inside that trip, like a small opening chapter. Everything we usually call old would become recent. The whole story of farming, writing, kings, trade, war, science, industry, and modern life would barely begin to measure the length of that motion through space. The names we know best would disappear almost immediately into the background. The longest-lasting buildings would crumble. Nations would change shape again and again. Even the languages used to launch the mission would almost certainly vanish long before the craft had traveled more than a small fraction of the full distance. And then there is the human body itself. A long human life might reach 80 or 90 years. Some lives end much earlier. A few stretch past 100. But even the longest life is only a tiny flicker beside a journey lasting hundreds of millions of years. A person could not meaningfully take such a trip in the ordinary sense. No crew could board a ship, look ahead toward a distant goal, and expect to arrive. The timescale is so large that the word traveler starts to lose its familiar meaning. If such a mission were ever attempted with present-day speeds, it would belong less to individuals than to chains of inheritance. Generation after generation would be born into it and vanish inside it. And even that picture may still feel too human, too small, because the number reaches beyond civilization and begins to overlap with the history of life itself. Hundreds of millions of years is long enough for entire groups of living things to appear, spread, change, and disappear. It is long enough for the surface of Earth to become unfamiliar. Long enough for coastlines to shift and climates to transform. Long enough for the world that launched the mission to become something no one on board could recognize, if anyone were somehow still there to compare it. A useful way to feel that scale is to place it beside the age of the dinosaurs. The dinosaurs lived long before us, and yet they do not belong to the beginning of Earth's story. They are one chapter in a planet that is more than 4.5 billion years old. Some of the great dinosaurs vanished about 66 million years ago. So when we say a journey might take hundreds of millions of years, we are speaking about spans of time several times larger than the distance between us and the last day of the dinosaurs. That is not ordinary distance with a few extra zeros added. That is distance expanding until it begins to behave like time on a planetary scale. And this is why the opening estimate matters so much. It is easy to hear a large number and assume it is just there for effect. But once we bring it down into history, lifetime, and memory, it stops sounding exaggerated. It starts sounding almost severe in its honesty. The Milky Way is so large that human beings become brief almost immediately. Our best machines, which seem bold and impressive near Earth, are reduced to something closer to a slow drift once they are measured against a galaxy. That feeling can be a little unsettling. We are used to asking how long something will take and expecting the answer to remain inside the world of practical thought. Days, months, years, maybe even decades. Here, the answer steps outside that world almost at once. It enters a range where the trip is no longer just difficult. It becomes detached from the ordinary rhythm of human continuity. And yet, even now, we are still standing at the edge of a deeper idea. Because all of this depends on what we mean by the Milky Way in the first place. The number feels overwhelming already, but it comes from a rough first picture, a simple image of a galaxy as a vast region you move through until you are finally beyond it. That picture is useful, but only as a beginning. To understand why escape becomes so difficult so quickly, we need to know what the Milky Way actually is. To understand why the journey becomes so extreme, it helps to stop picturing the Milky Way as a soft band of light and begin picturing it as a real place. On a clear, dark night, far from city lights, the Milky Way looks like a pale river spread across the sky. For most of human history, that glowing band was all anyone could see. It looked beautiful, mysterious, and distant, but it did not yet look like something with shape. It did not look like a system you could be inside. Now we know that the Milky Way is a galaxy, and a galaxy is not just a loose scattering of stars. It is a huge organized structure held together by gravity. It has a broad disk, spiral arms, a crowded central region, and a vast outer reach that stretches much farther than the bright part most people imagine when they hear the name. That disk is the part that gives the Milky Way much of its familiar form. If you could rise far above the galaxy and look down on it, you would not see a straight band at all. You would see a great spinning disk of stars, gas, and dust, shaped somewhat like a flattened whirlpool. Curving through that disk are spiral arms, long sweeping regions where stars, clouds, and darker lanes of dust help give the galaxy its graceful shape. Our view from Earth is strange because we are inside that disk rather than above it. We are looking through the crowded plane of the galaxy from within, which is why the Milky Way stretches across the sky as a glowing strip, instead of appearing as a full spiral. It is the difference between looking at a forest from above and standing deep among the trees. From the ground, the full shape disappears. You see only layers, distance, and density. At the center of the Milky Way, the galaxy grows thicker and brighter. This region is called the bulge. It is packed with many more stars than the quieter part of the disk, where our solar system lives. Deep in that central region sits a supermassive black hole called Sagittarius A star. It does not swallow the whole galaxy the way people sometimes imagine, but it marks the crowded, powerful heart of the system. Around the disk and central bulge, the galaxy also has a much larger surrounding region called the halo. This is where the Milky Way begins to feel less like a bright spinning city of stars and more like a vast, thin outer domain. The halo contains some stars, clusters of stars, hot gas, and most importantly, much of the galaxy's hidden mass. That hidden mass matters because the Milky Way is not made only of what shines. A great deal of its gravity comes from dark matter, which does not glow, but still helps shape the galaxy and hold it together. That means the Milky Way is larger than it looks. The bright part, the part most people picture first, is only the most visible region. Beyond that glowing disk is a wider structure, and beyond the most obvious stars is still more of the galaxy's reach. So the Milky Way is not a flat picture pasted onto the sky. It is layered. It has a denser middle, a broad spinning body, and a more extended outer region that becomes harder to see but no less important. This changes the feeling of the question almost immediately. Once the Milky Way becomes a place with structure, the journey no longer feels like heading toward a simple edge. It starts to feel like moving through a system with depth, shape, and hidden extent. The glowing band we see at night is only one view from one position inside something much larger. And that inside part matters. We are not looking at the Milky Way from a safe distance. We are living within it. The sun, the planets, the dust of Earth, every ocean, every city, every living thing, all exist as part of this larger galactic structure. The Milky Way is our cosmic environment in the same way Earth is our planetary one. We are inside its disk, moving with it, surrounded by its stars, and held by its gravity, whether we notice it or not. That is where the image begins to sharpen. The Milky Way is no longer just something overhead. It becomes the enormous system around us, above us, below us, and far beyond us. It becomes the setting of the journey itself. And once that setting is real, the next question becomes much more precise. If this galaxy has a shape, a center, a disk, and a wider reach beyond the bright stars, where exactly are we inside it? Once the Milky Way begins to feel like a real place, the next thing we need to know is where we are inside it. That matters more than it may seem at first. If Earth were sitting near the outer edge of the galaxy, then leaving might sound difficult, but still somewhat straightforward. We would already be close to the boundary. We could imagine turning outward and beginning the final stretch. But that is not where we are. The solar system lives well inside the Milky Way. We are not near the bright, crowded center, which is filled with many more stars and much stronger galactic density. But we are also nowhere near being outside the galaxy. We sit in the disk, inside one of the spiral arms, at a distance of about 26,000 light-years from the galactic center. That places us in a middle region, far from the heart, but still deep within the larger structure. A helpful way to picture this is to imagine living inside a vast city. You do not live downtown, in the most crowded and intense part of it, but you also do not live at the last quiet house on the edge of town, where the road simply ends and open land begins. You live somewhere out in the city, in a place that may feel less dense than the center, but is still firmly part of the whole system. To leave, you still have a very long way to go. That is our situation in the Milky Way. The galaxy's disk is often described as being around 100,000 light-years across, though the exact number depends on what part of the galaxy we mean and where we draw its brighter limits. From where the sun is located, the distance inward to the center is already immense. The distance outward to the visible outer regions is also immense. There is no sense in which we are almost there. We are starting from inside, and that simple fact shapes everything. Our position also helps explain why the Milky Way looks the way it does from Earth. Because we are inside the disk, looking along it, we see many more stars spread across that flattened galactic plane. That is why the Milky Way appears as a glowing band across the sky, rather than a distant spiral shape. We are seeing our local view from within the structure itself, surrounded by stars in some directions more densely than others, with dust clouds blocking portions of the light and making the band look uneven and textured. So even our night sky quietly tells the truth about our position. We are embedded in the system. We are not standing outside it, looking back with a clear map in hand. We are inside the moving disk, orbiting with the sun, seeing only the local view from a small and ordinary place in one spiral arm. And the sun is moving too. Our solar system is not parked in one spot. It is orbiting around the galactic center at an enormous speed, taking roughly 225 to 250 million years to complete one full orbit. Sometimes this is called a cosmic year or galactic year. That means that since the dinosaurs disappeared about 66 million years ago, the Sun has not even completed one full lap around the center of the Milky Way. That is another useful anchor. We often think of galaxies as still pictures, as if stars are fixed in place and we are simply choosing where to go within them. But our starting point is already in motion. Earth, the Sun, and the rest of the solar system are all being carried around inside the galaxy as part of its larger flow. So the journey outward does not begin from a quiet, motionless platform. It begins from a moving location inside a rotating system. That deepens the challenge in a subtle way. Leaving the Milky Way is not just about aiming away from the center and heading off into darkness. It means starting from a position that is already far inside the galaxy, already bound to its motion, and already separated from anything like an outer edge by distances so large they are hard to hold in the mind for long. This is why the opening number grew so quickly. It was not only because the galaxy itself is large, it was also because we are starting from within it, from a place that feels local to us only because it is home. Home can make scale feel smaller than it really is. But once we step back and look at our true position, the shape of the problem becomes much more serious. We are not preparing for a short climb out of the galaxy. We are preparing, at least in thought, for an outward journey from deep inside a structure vast enough to make even our starting point feel remote. And once that starting point is clear, the next question follows almost automatically. How far is it from where we are to anything that could honestly count as outside? Once our position is clear, the next step is to give the journey a shape. It is one thing to say we want to move outward from the Milky Way. It is another thing to ask how far outward that really is. Without a distance, the idea remains loose. It feels like pointing into darkness and saying somewhere over there. But space becomes much easier to understand once direction turns into distance. From where the solar system sits, about 26,000 light-years from the galactic center, the path outward to the brighter edge of the Milky Way is not a short final stretch. It is still a journey of tens of thousands of light-years. That point is worth sitting with for a moment. A single light-year is the distance light travels in 1 year, moving at about 300,000 kilometers every second. Light is so fast that it can go around Earth more than 7 times in a single second. And yet, even with that speed, it still takes over 4 years for light to reach the nearest star system beyond our own. So when we begin stacking distances in the tens of thousands of light years, we are moving into a range that no ordinary form of travel language was designed to handle. From our region of the galaxy, heading outward through the disk toward the farther visible reaches, means crossing something like 20,000 to 30,000 light years, depending on the exact direction and where we choose to treat the bright outer galaxy as beginning to thin away. That gives the problem a real span. We are no longer imagining a vague departure from home. We are imagining a trek across a meaningful fraction of the Milky Way itself. This is where the geometry of the situation starts to matter. The Milky Way is often pictured from above as a broad spiral disk. If you place the center in the middle and then mark the sun partway out from that center, you can begin to see the challenge clearly. We are not at the hub, and we are not near the rim. We are somewhere between them. To reach the outer visible parts, we would need to move across a large slice of the galaxy's width. To go farther still, beyond the familiar body of stars, would mean continuing past that bright disk into more remote territory. So the journey has direction, but it also has depth. It is not a matter of rising a little above the galactic plane and suddenly being free. If we are speaking in broad, understandable terms, escape begins as a very long outward crossing from an interior position toward the Milky Way's far side. And because our starting point is already so deep within the system, even the first part of that movement is enormous. A helpful comparison is to imagine standing in the middle region of a continent and deciding to walk to the shore. If you are already near the coast, the sea feels close, even if the walk is tiring. But if you are far inland, then the same idea becomes something much larger. The coast is still real, still reachable in theory, but it belongs to a different scale of travel. That is what happens here. The word outside sounds simple because it feels like it should describe a nearby boundary. Yet from where we are, outside the Milky Way begins only after crossing distances so large that the galaxy must first become a map in the mind. You need to picture a center behind us, outer regions ahead of us, and our own small location between those two extremes. Once you do that, the trip stops feeling like a loose cosmic thought and starts to feel like a line drawn across a giant structure. And that line is long. Even at the speed of light, crossing 20,000 or 30,000 light years would take 20,000 or 30,000 years. That alone tells us something powerful. Light itself, the fastest thing we know, does not treat this as a short journey. So any human-made object moving far more slowly immediately inherits that difficulty in a much harsher form. This is why the first estimate landed in such deep time. The destination was never just a point somewhere in the dark. It was always a vast outward span from an interior location to a distant boundary that is itself not easy to define. And that last detail matters more than it first appears. Because once the Milky Way becomes a real distance to cross, a new uncertainty rises almost immediately. We can measure our position. We can picture the broad path outward. We can estimate the span to the visible outer regions. But a galaxy is not a wall, and it does not end like a road. So before we can say what it really means to get beyond it, we have to ask a more careful question. Where does the Milky Way actually stop? That is where the journey becomes a little more subtle. A distance can be measured. A direction can be drawn. But an edge is a different kind of thing. We are used to edges that behave clearly. A coastline separates land from sea. A wall separates one room from another. Even the atmosphere of Earth, though gradual in some ways, feels like it gives way to space with a recognizable change. The Milky Way does not offer that kind of ending. When people picture a galaxy, They often imagine a bright spiral with a visible outer rim, as though the stars simply stop at a certain point and the rest is empty. From far away, that image can be useful. It helps the eye understand the general shape. But once we ask where the galaxy truly stops, the answer becomes less tidy. The bright disk has an outer reach where stars become fewer, and the clear spiral structure begins to thin. If you were looking at the Milky Way from a great distance, this brighter body would be the first thing you noticed. It would feel natural to call that the galaxy. In that sense, one possible meaning of leaving the Milky Way would be to travel beyond the main visible disk, far enough that the dense, glowing body of stars is behind you. That is a reasonable first idea. But galaxies are not made only of the parts that shine most clearly. Beyond the brighter disk, the Milky Way continues in thinner and less obvious ways. There are older stars scattered farther out. There are globular clusters orbiting in the wider surroundings. There is hot gas extending beyond the main body. And there is the much larger dark matter halo, a broad region of hidden mass that does not glow but still helps shape the galaxy and hold it together. So if someone says they have left the Milky Way because they are beyond the obvious spiral body, that may be visually true in one sense. The galaxy would no longer surround them as a dense field of stars in the same way. The bright disk would have fallen behind. The view might already feel lonely and remote. But visually outside and physically outside are not always the same thing. That distinction matters because it changes the meaning of the journey. If we are satisfied with leaving the bright, familiar body of the galaxy, then the target is one thing. If we mean leaving every important part of the Milky Way's larger structure, then the target moves farther outward. And if we mean escaping the galaxy in the deepest physical sense, then the question may have less to do with visible boundaries at all, and more to do with gravity. This is what makes the Milky Way such a strange destination. It has layers of ending. There is the point where the bright disk begins to thin. There is the broader region where stars become much more sparse. There is the halo, where the galaxy still has presence even when it no longer looks like the familiar Milky Way of photographs and diagrams. And surrounding all of this is a larger gravitational reach that does not announce itself to the eye. So the word outside begins to split into several meanings. A traveler could move beyond the bright spiral body and feel outside in an ordinary visual sense. The galaxy would no longer appear as a place they are immersed in. It would begin to look more like an object behind them. That experience would be real. It would matter. It would mark a change. Yet the deeper story would remain unfinished. Because space does not care only about what looks finished to us. A galaxy is not merely a picture. It is a system. It extends beyond its brightest parts, and some of its most important boundaries are not boundaries in the usual sense at all. They are gradual transitions, fading structures, and invisible influence. That makes the destination fuzzier, but also more interesting. The problem is no longer just how far we must go. It becomes which version of departure we mean. Are we trying to leave the crowded visible galaxy behind? Are we trying to pass beyond the broader stellar body? Or are we trying to become truly free of the Milky Way as a physical system? Those are not identical goals. And once that becomes clear, the journey changes shape again. A simple outward line across the disk is still useful, but now it begins to feel like only the first layer of the story. Leaving the visible galaxy might be dramatic and meaningful, but it may still fall short of the deeper kind of escape we are really trying to understand. Because a galaxy can still hold you long after it stops looking like home. And that leads to the next question almost naturally. If we move beyond the visible part of the Milky Way, have we truly escaped at all? That deeper kind of escape begins with a quiet correction. A ship can travel a very long way from the familiar stars and still not be free. From a human point of view, that may sound strange at first. We are used to thinking visually. If a traveler leaves the bright part of a city behind, then they have left the city. If a plane crosses beyond the coastline, then it has left the land. Our eyes are often good enough to tell us when a boundary has been crossed. A galaxy is more deceptive than that. The bright disk of the Milky Way is the part that announces itself most clearly. It is where stars are packed more densely, where dust lanes cut through the light, and where the galaxy looks full and richly structured. If a spacecraft kept moving outward long enough, there would come a point where that dense brightness began to thin away. The sky behind the ship would still contain stars, but the Milky Way would no longer feel like a glowing world wrapped all around the traveler in the same way. The galaxy would begin to look more distant, more contained, more like something being left behind. That would feel like departure. And in one sense, it would be. But physical escape asks a different question. It asks whether the spacecraft has moved far enough and fast enough that the Milky Way can no longer pull it back as part of its own system. That is a much stricter idea. It means that distance alone is not enough. A ship can be very far away and still remain gravitationally bound, still following a path that belongs to the galaxy, rather than truly breaking free from it. This is easier to understand if we start closer to home. Think about Earth and the Moon. A spacecraft can rise far above Earth's surface and still be in Earth's gravitational grip. It may be high enough that our planet looks smaller, high enough that the atmosphere is gone and the darkness of space surrounds it. But none of that means escape has happened. To actually leave Earth behind, the spacecraft needs enough speed to overcome Earth's pull. The same logic works at the scale of the solar system. A probe can travel far from the Sun and still remain part of the Sun's wider gravitational domain. The Milky Way works the same way, only on a vastly larger scale. The galaxy is not just a collection of visible stars scattered through darkness. It is a gravitational system with enormous mass. That mass includes the stars we can see, the gas and dust spread through the disk, and the much larger dark matter halo extending far beyond the bright spiral structure. All of that mass helps shape the galaxy's pull, so even if a spacecraft moves beyond most of the bright disk, it may still be deep inside the Milky Way's larger grip. This changes the meaning of the journey in a powerful way. Leaving the visible galaxy may create the feeling of escape, but the feeling is not the same as the physics. The stars could be thinning. The disk could be shrinking behind the ship. The traveler might look back and see the Milky Way as a more contained object in the sky. And still, the craft could remain part of the galaxy's story, still moving through space on terms the galaxy has set. That is the quiet turning point in the question. The first version of leaving was based on sight. It asked how far we would need to go until the Milky Way no longer looked like the environment around us. This newer version is based on freedom. It asks when the galaxy loses its hold over the ship's motion itself. Those are two very different thresholds. One is about appearance. The other is about whether you still belong to the system you are trying to leave. Once that difference is clear, the journey feels more serious again. The visible disk, vast as it is, becomes only one layer of the challenge. A ship might cross that layer and still not be truly outside in the deeper physical sense. The Milky Way can continue beyond what the eye finds obvious, and its influence can continue beyond what the mind first pictures. So the question becomes more exact. We are no longer asking only how far it is to the thinning edge of the stars. We are asking what kind of motion would finally carry a spacecraft beyond the Milky Way's control. We are asking what it really means to stop orbiting within the system and begin moving independently of it. And that kind of escape depends on something more than distance. It depends on speed. That is where the journey stops being only a matter of miles or light years and becomes something deeper. A ship does not truly escape the Milky Way just by drifting far enough away from the bright stars. It escapes when the galaxy no longer owns its path. That idea sits at the heart of the whole problem. Gravity is not simply a force that pulls things straight inward like a rope. In large systems, it shapes motion. It decides which objects remain bound, which ones orbit, and which ones finally move with enough freedom to leave. Earth circles the Sun because the Sun's gravity holds it in a long curved path. The Moon circles Earth for the same reason. Our solar system itself moves within the Milky Way because the galaxy's mass is shaping our motion too. So when we ask what it would take to leave the Milky Way for real, we are really asking when a spacecraft stops being one more object moving under the galaxy's grip. That depends on velocity. If a spacecraft starts from our region of the galaxy and simply heads outward at too low a speed, it may travel for an enormous distance and still remain bound. Its path may stretch far into the outer parts of the Milky Way, but the galaxy would still be shaping that motion. In time, the craft might slow, curve, or remain part of a very long galactic trajectory rather than becoming truly free of the system. That is the deeper rule. Distance tells us how far the trip extends. Velocity tells us whether the trip counts as escape at all. A helpful way to picture this is to imagine throwing a ball upward from Earth. If you toss it gently, it rises and falls back. If you launch it harder, it climbs higher before falling. If you launch it fast enough, it never returns. The first two throws differ in height, but they are both still under Earth's control. The third reaches escape velocity. That is the threshold where the path stops belonging to Earth. Galactic escape works on the same principle, only at a far greater scale. The Milky Way is full of mass. There are hundreds of billions of stars, enormous clouds of gas and dust, and a dark matter halo reaching far beyond the part of the galaxy we can easily see. All of that mass contributes to the galaxy's gravity. That means escaping the Milky Way is not about finding the place where the stars become sparse and stepping beyond it like crossing a border. It is about moving fast enough that the galaxy can no longer keep you as part of its larger motion. This is why the problem becomes more demanding the more carefully we define it. A ship might make the Milky Way look smaller behind it. It might enter darker regions where the dense disk has faded into a more distant structure. And still, from the galaxy's point of view, it could remain bound. It would still belong to the system in the same basic way a comet can travel far from the Sun and yet still remain part of the solar system. That comparison helps because it shows how misleading appearances can be. A comet at great distance may feel almost gone, but gravity has a longer memory than our eyes do. The Milky Way works that way too. Its visible body may fall away, while its influence continues. So the real barrier is not the last bright patch of stars. The real barrier is the speed needed to break free from the galaxy's hold. That is what turns this from a giant road trip into a physical threshold. Once velocity enters the story, the question becomes sharper and in some ways harsher. We are no longer only asking how long it takes to cross a great span. We are asking whether our motion is enough to escape a system built from vast amounts of mass. And that changes how we think about our own place in the galaxy as well. The Sun is already moving around the Milky Way at a tremendous speed, carrying Earth with it. We do not notice it in daily life, but we are already part of a larger galactic flow. A spacecraft leaving from Earth does not begin from rest in some quiet cosmic stillness. It begins inside an active moving system, and any true escape must overcome the fact that we are already bound into that motion from the start. So the question narrows into something more exact. How much speed does a spacecraft actually need if it wants to leave the Milky Way in the deepest physical sense? Not just pass beyond the brightest stars, but truly stop belonging to the galaxy's pull. Here is where the problem becomes more demanding than it first appeared. Up to this point, it has been possible to imagine the Milky Way as a huge distance that could, in theory, be worn down with patience. If the galaxy is large enough, then perhaps escape is simply a matter of continuing outward for long enough. But once gravity and motion enter the picture fully, patience stops being the main issue. A ship does not earn freedom just by spending a long time traveling. It has to be moving fast enough for the galaxy to truly lose its hold. And that required speed is very high. The exact number depends on how the Milky Way's mass is modeled, especially the part we cannot see directly, like the dark matter halo surrounding the galaxy. But from our part of the Milky Way, astronomers estimate that escape requires a speed on the order of about 500 to 600 kilometers per second relative to the galaxy. A commonly cited value is around 550 kilometers per second. That is the kind of number that changes the whole mood of the journey. 550 kilometers per second means covering about 33,000 kilometers every minute. It means crossing a distance roughly equal to Earth's circumference in a little over 1 minute. It means moving at nearly 2 million kilometers per hour. By human standards, it is almost absurdly fast. And yet, in galactic terms, it is simply the speed needed to stop belonging to the Milky Way as a bound object. This does not mean a ship must fire its engines forever at exactly that speed, as though aiming for a magical line in space. It means that if the craft's total motion through the galaxy is below the escape threshold, then however far it wanders outward, it still remains part of the Milky Way's larger gravitational story. It has traveled far, but it has not broken free. A useful way to picture this is to imagine a deep valley. If you roll a ball uphill gently, it may travel a surprising distance before slowing and turning back. Roll it harder, and it climbs farther. But unless it has enough energy to clear the valley entirely, it still belongs to the valley. Galactic escape works the same way. A spacecraft can move outward through a vast stretch of space and still never truly leave if it lacks the speed needed to rise beyond the galaxy's gravitational depth. That idea makes the challenge feel more exact. The Milky Way is no longer just a region with a center and an outer edge. It is a system with a threshold. Below that threshold, motion remains trapped in one form or another. Above it, escape becomes physically possible. So there is a sense in which the galaxy has two kinds of size. There is the visible size, the one we imagine when we picture stars spread across a spiral disk. And there is the gravitational size, the one expressed through how much speed it takes to get away. The second size is the more serious one. It is also tied to where we begin. We are not launching from empty intergalactic space. We are launching from Earth, carried by the Sun, already moving inside the Milky Way. That means any true escape attempt begins from within a living system of motion. The starting point matters. The speed needed from our region of the galaxy is not a universal number that applies everywhere in the same way. It belongs to where we are, how mass is distributed around us, and how deeply inside the Milky Way we still sit. Once that sinks in, the early estimate from the beginning of the documentary starts to feel almost gentle. At first, the trip seemed overwhelming because the distance was so large. Now the trip becomes even harsher because distance was only half the problem. A ship could head outward across astonishing spans of space and still fail in the deeper sense if it never crossed the escape speed threshold. The galaxy would still, in its own quiet way, be keeping the ship. That is what makes this more than simple travel math. It is the difference between wandering far from home and actually ceasing to belong to home's gravitational pull. One is a matter of scenery. The other is a matter of physics. And physics is less forgiving than appearances. So the question sharpens again. If the Milky Way asks for something like 550 kilometers per second from our region in order to truly escape, then how close are we really? What is the fastest speed humanity can actually reach in 2026? And how small does that speed begin to look once we place it beside the galaxy's demand? Once that escape speed is placed beside our own machines, the scale of the gap becomes much easier to feel. Human beings have built remarkable spacecraft. We have sent probes past every major planet in the solar system. We have landed on the moon, touched asteroids, flown through the atmosphere of Titan, and sent instruments beyond the outer planets into interstellar space. Near Earth, these achievements feel enormous, and they are. They represent centuries of learning, engineering, and persistence. But the Milky Way is not a local problem. It does not measure us by what is impressive near Earth. It measures us against the depth of a galaxy. One of the fastest spacecraft humanity has ever launched is the Parker Solar Probe. During its closest passes to the Sun, it reaches speeds of around 190 kilometers per second, and at times even more than that. Voyager 1, which has become a symbol of deep space travel, moves much more slowly, at about 17 kilometers per second relative to the Sun. New Horizons, which flew past Pluto and continued onward into the Kuiper Belt, travels at roughly 14 kilometers per second after its escape from the inner solar system. These are astonishing speeds in any human setting. A machine moving at 17 kilometers per second would cross the United States in a few minutes. A craft moving near 190 kilometers per second would leave Earth and most familiar human scales far behind almost instantly. It is easy to see why such numbers feel extreme to us. They are extreme. And yet the Milky Way quietly makes them look smaller. If true galactic escape from our region requires something like 550 kilometers per second, then even Parker Solar Probe, our fastest spacecraft, still falls far short of that threshold. it reaches only about a third of the speed needed. Voyager 1, the probe people most often picture when they imagine humanity reaching out into the dark, is slower by more than an order of magnitude. It is moving at only a small fraction of what the Milky Way demands for full escape. That comparison changes the emotional weight of the whole question. At first, it is tempting to think that because we already send probes far beyond Earth, and because space technology keeps improving, perhaps the difference is only one of time and patience. But this is where the numbers become stern. Our best machines are not a little short. They are deeply short when measured against the galaxy's gravitational scale. A useful way to feel this is to imagine a mountain tall enough that climbing halfway up would still leave you far below the summit. Parker Solar Probe is extraordinary. It is the most extreme speed humanity has achieved with a spacecraft. Yet against the Milky Way's escape requirement, even that achievement begins to look like a partial ascent rather than a crossing. And Parker's speed comes with an important detail as well. It reaches those extreme numbers by falling deep into the Sun's gravity well during close passes. That is different from a spacecraft simply cruising through deep space at that same speed under its own power. In other words, the fastest speeds we have achieved are often tied to very special conditions. They are real, but they do not automatically mean we are ready to launch a galaxy-escaping ship from Earth and send it cleanly outward into interstellar space. So the gap is not only numerical, it is practical. Voyager 1, New Horizons, and our other deep space probes prove that we can leave planets behind. Parker Solar Probe proves that we can push spacecraft to extraordinary speeds under certain conditions. But none of these missions come close to solving the deeper challenge of escaping the Milky Way in the strict physical sense. They are local triumphs facing a galactic standard. This does not make them less meaningful. In some ways, it makes them more meaningful. They show what a young technological species can already do. But they also reveal how quickly cosmic scale can humble us. A spacecraft that feels bold and almost unbelievable within the solar system can still look slow once the frame expands to the size of a galaxy. That is the gap we have arrived at. On one side is the speed the Milky Way seems to require. On the other is the speed humanity can actually reach in 2026. Between those two lies a difference large enough to reshape the entire journey. It means the first estimate we opened with, already immense, may have been kinder than the fuller reality deserves. Because once our best real speeds are placed beside the galaxy's demand, the original timeline has to be looked at again with sharper eyes. And that raises the next question naturally. If humanity's fastest spacecraft fall this far below what the Milky Way asks of us, what happens to the travel time when we stop using rough intuition and begin using our actual limits? With that comparison in place, the opening estimate begins to feel like a kind first draft. It served its purpose. It gave us a real anchor early on. It showed that even a simple outward journey from our part of the galaxy already belongs to timescales far beyond normal human thought. But now that we have built a clearer picture of what the Milky Way is, where we are inside it, and what true escape means physically, we can see that the first answer left out something important. It treated escape as though distance were the main burden. Distance is still a huge part of the story. There is no getting around that. Tens of thousands of light years remain tens of thousands of light years, no matter how carefully we define the problem. But the moment we ask for something stricter than merely reaching a dimmer, emptier region of space, the calculation changes. The journey is no longer just about crossing a span. It becomes about crossing that span while moving in a way that actually frees the spacecraft from the Milky Way's gravitational hold. And once that standard is applied, the opening number starts to look generous. A simple estimate based on current human deep space speeds and a rough outward distance can land in the range of hundreds of millions of years. That estimate is useful because it tells the truth about scale. But it also carries an unspoken softness. It assumes that going outward and going free are close enough to treat together. By now, we know they are not. A ship moving at Voyager 1 speed, around 17 kilometers per second, could certainly keep heading away from the galactic center for an unimaginable length of time. It could move through deep darkness, leave many familiar stars behind, and travel farther than any human-made object has ever gone. Yet in the deeper physical sense, that motion is still nowhere near what the Milky Way seems to require for real escape. It would be outward travel, yes, but outward travel under conditions that leave the spacecraft bound to the system. That is what makes the difference feel so severe. The first answer told us how large the galaxy is. The revised answer tells us how demanding the galaxy is. These are not the same lesson. A very long travel time can still belong to the world of patient crossing, as though the universe were simply giving us an absurdly long road. But once we add the escape speed threshold, the road becomes something more like a climb out of a gravitational valley. The spacecraft is not simply moving across space. It is trying to carry enough motion to stop being claimed by the galaxy itself. That means the first number, however shocking it sounded, was closer to a lower level anchor than a final truth. It described one broad version of departure. It did not yet fully capture the harder version, the version in which escape means genuine freedom from the Milky Way as a bound system. And the harder version deepens the timeline in more than one way. It is not just that a higher required speed makes our present machines look inadequate. It is also that our fastest real probes do not cruise through deep space at anywhere near the level needed. Voyager 1, New Horizons, and other great missions prove that we can leave the planets and reach the outer dark. Parker Solar Probe shows that human engineering can touch extraordinary speed under very special conditions near the Sun. But none of these achievements remove the basic fact that, by galactic standards, we are still operating far below escape scale. So the opening estimate remains true in spirit, but incomplete in severity. It told us the trip was almost unimaginably long. The clearer model tells us something more sobering. The trip is not merely long because the galaxy is wide. It is long because the definition of success is harsher than simple distance, and because the speeds required for real success remain far beyond what our present technology can deliver in any clean, practical way. That is where the question begins to shift again. Up to now, we have let current human capability set the terms. That has been useful because it keeps the problem honest. It keeps us anchored in what can truly be done in 2026. But it also leaves a natural opening. If present-day spacecraft fall so far short, perhaps the real change would not come from refining the estimate again and again. Perhaps it would come from changing the machine itself. And once that possibility enters, the next thought follows almost on its own. If current propulsion leaves us trapped inside these immense timelines, could a very different kind of engine meaningfully change the answer? From here, it becomes tempting to imagine a better engine sweeping the whole problem away. That instinct makes sense. If the main obstacle is speed, then a faster spacecraft feels like the obvious answer. And in one important way, it is. Better propulsion would change the journey dramatically. It could shrink timelines that currently feel impossible. It could move galactic escape out of the range of deep evolutionary time and into something at least easier to picture. But once we begin testing even ambitious future ideas, the Milky Way still refuses to become small. A useful place to start is with the difference between faster than today and fast on a galactic scale. Today, our deep space probes move at tens of kilometers per second. That is enough to cross the solar system over time, but far below what true galactic escape seems to demand. So the first leap forward would be to imagine propulsion systems that can push spacecraft not to tens of kilometers per second, but to hundreds. At that point, we begin entering the same broad range as the escape speeds discussed earlier. Nuclear propulsion is one of the first ideas that often appears here. Human beings have studied nuclear thermal rockets and other nuclear-powered concepts for decades. These engines would not behave like ordinary chemical rockets. They could provide far more energy and, in principle, drive spacecraft to much higher speeds. Fusion, if it ever becomes practical for propulsion, could go farther still. Antimatter is even more extreme as a concept, though far more difficult to handle in reality. Then there are beamed propulsion ideas, where a sail or lightweight craft is pushed by powerful lasers or other external energy sources, rather than carrying all its fuel on board. Each of these ideas opens the same door. They make it easier to imagine velocities that no present-day spacecraft can maintain in deep space. And once those velocities rise, the timeline changes very quickly. A trip that might take hundreds of millions of years at Voyager-like speed can fall to tens of millions, then millions, then perhaps far less depending on how close we get to a meaningful fraction of the speed of light. The numbers begin to soften. The journey becomes less like the lifespan of entire branches of life on Earth, and more like something that belongs to long civilizations, distant descendants, or engineered futures. That is a real change. It matters. If a spacecraft could somehow travel at 1% of the speed of light, about 3,000 kilometers per second, then tens of thousands of light years could be crossed in millions other than hundreds of millions of years. At 10% of light speed, the same broad galactic distances begin to fall into the range of hundreds of thousands of years. Those are still immense spans, but they no longer belong to the same crushing scale as the opening estimate. So hope does enter the story here. The galaxy does become less overwhelming when the engine improves, but only less overwhelming. Even very optimistic propulsion does not turn the Milky Way into a local trip. 100,000 years is still longer than all of recorded human history many times over. 1,000,000 years is still long enough for species to change and landscapes to transform. Even a craft moving at 1/10 the speed of light would not make galactic escape feel ordinary. It would only move the problem from impossible in one way to extreme in another. And the more ambitious the engine becomes, the more the rest of the mission begins to matter. A propulsion breakthrough solves one kind of difficulty, but it also exposes how many other burdens were hiding underneath the speed problem. A ship moving through interstellar space at very high velocity is not simply enjoying a cleaner, shorter version of the same trip. It is entering a harsher environment. Dust grains become dangerous. Radiation becomes a deeper concern. Energy demands become enormous. The spacecraft itself becomes harder to build, harder to protect, and harder to keep alive across long spans. So better engines do not cancel the scale of the Milky Way. They reveal it in a new way. They show that speed was never the whole story, even if it was the first and most obvious barrier. The galaxy remains large enough that, once propulsion improves, the challenge simply shifts to whatever problem has now become the weakest point in the chain. That shift is important because it keeps the documentary honest. It prevents the story from turning into a simple fantasy where one miraculous machine solves everything. A better engine would be transformative. It would change the math in ways that truly matter. But the Milky Way is large enough, and space is harsh enough, that changing the engine does not make the journey easy. It only changes which part of the journey frightens us most. And that is where the next layer begins to rise. If future propulsion can soften the timeline, but not erase the difficulty, then what takes over as the real danger once speed is no longer the main limitation? Even with a better engine, space does not suddenly become gentle. A faster ship would cut the timeline. And that matters. But it would also bring a different kind of trouble into focus. The journey would stop feeling like a problem of waiting and start feeling like a problem of surviving. At high speeds, the emptiness between stars is not truly empty, and the things scattered through it begin to matter in a much harsher way. Interstellar space contains gas, dust, charged particles, and radiation. Most of it is spread very thinly. If you move through it slowly enough, that thinness feels comforting. It makes the space between stars seem open and quiet. But the faster a spacecraft moves, the more dangerous even tiny particles can become. A grain of dust at ordinary human speed is nothing special. A grain of dust striking a ship at a large fraction of interstellar speed becomes something else entirely. It carries far more energy, and that energy has to go somewhere. It can erode surfaces, damage shielding, and threaten anything exposed at the front of the craft. This is one of the strange lessons of deep space travel. Speed saves time, but speed also makes the road more violent. Radiation adds another layer of risk. Space is already full of energetic particles from the sun, from distant events in the galaxy, and from the broader universe itself. Earth protects us with its atmosphere and magnetic field. A spacecraft heading out into deep interstellar space loses those protections. Over a long mission, radiation exposure becomes a serious problem for electronics, materials, and living tissue. A ship can shield against some of this, but shielding means extra mass, and extra mass makes propulsion harder. The faster and longer the mission becomes, the more every design choice starts leaning against every other one. Energy demand deepens the problem further. A powerful engine is not just an idea on paper. It has to be fed, controlled, cooled, and trusted. If the craft carries fuel, then that fuel adds weight. If it depends on external energy, like a beamed propulsion system, then the infrastructure needed to launch and guide it becomes enormous. If it uses nuclear systems, then those systems must operate safely for very long periods, far from repair crews or rescue. A mission that sounds elegant in a short description can become brutally complicated once the real hardware enters the picture. And then there is reliability. A spacecraft going to Mars can fail after months and still be part of a mission humans can understand. A spacecraft going beyond the galaxy enters another category. Every system on board would need to work not only at launch, but across spans of time that defeat ordinary expectations. Guidance, power, heat control, communications, structure, shielding, life support if humans are present. All of it would need to keep functioning in a place with no harbor, no emergency landing, and no nearby help. That changes the emotional shape of the mission. It is no longer just a long line through a dark map. It becomes a moving world exposed to a slow, relentless environment. Tiny failures matter, small leaks matter, material fatigue matters, a sensor breaking in the wrong place matters. On a short mission, breakdown is a setback. On a galactic mission, breakdown can become destiny. The deeper we go into the problem, the more the galaxy reveals its terms. First, it asks for distance. Then it asks for speed. Then, once speed begins to improve, it asks for endurance under conditions that are difficult to soften. The progress is real, but it comes with a price. A better engine does not remove danger. It often intensifies it by forcing the ship into a harsher relationship with the space around it. That is why the mission begins to feel less like a triumph of raw power and more like a test of total systems thinking. The engine matters, but so do materials, shielding, navigation, long-term maintenance, and the quiet ability to keep going through an environment that does not care whether the ship is fragile. And once that is clear, the next question becomes less about machinery and more about us. If the voyage is shaped by radiation, impact risk, extreme engineering demands, and reliability across unimaginable spans, could human beings themselves survive a mission built on terms like these? By the time the dangers become clear, the spacecraft has already started to change in our minds. It no longer feels like a machine built to carry a few travelers from one point to another. The distances are too large, the risks are too steady, and the passage of time is too deep for that kind of thinking to hold. A realistic vessel for a journey like this would have to become something larger. It would have to become a place where human life could continue, not just survive briefly, but continue in a stable way for spans that reach far beyond an ordinary mission. That changes everything. A normal spacecraft is built around a temporary goal. It carries fuel, instruments, power systems, life support if needed, and a plan to complete a mission within a period people can still grasp. A galactic escape vessel meant for human beings would have to do more than protect a crew. It would have to support a living world inside itself. That means air that can be renewed, water that can be recycled, food that can be produced or stored across extreme timescales, and systems that do not merely function, but function reliably while surrounded by isolation. Even waste becomes part of the design. Heat becomes part of the design. Illness becomes part of the design. Repair becomes part of the design. The ship could not be a sealed can drifting through the dark. It would need to behave more like an environment. The moment that happens, the mission stops looking like transportation and starts looking like civilization in miniature. People on board would need shelter, but also structure in the broader sense. They would need routines, knowledge, tools, education, medicine, and social continuity. A child born on such a vessel would not experience it as a craft heading somewhere. They would experience it as the world they live in. The walls, the lights, the recycled air, the food systems, the maintenance spaces, all of that would form the reality of daily life. The destination might remain intellectually important, but life would still have to be lived one ordinary day at a time inside the ship itself. That is what makes the design problem feel so much larger. You are no longer building an engine strong enough to move through space. You are building a world stable enough to carry human life through time. And worlds are harder to build than vehicles. A living system must keep balance. Air cannot drift too far from what bodies need. Water must remain clean. Food systems must recover and continue. Materials wear down. Machines break. Knowledge must be preserved and taught. There must be enough redundancy that one failure does not bring everything down with it. A ship like this could not depend on the idea that specialists back on Earth will simply fix problems later. It would have to carry repairability within itself, and likely the ability to make new parts, adapt old ones, and teach future generations how to keep everything working. Storage becomes more complicated too. If the mission lasts long enough, storing everything in finished form may not be enough. Food, medicine, and spare parts all have limits. Some things degrade. Some things run out. So the ship may need gardens, manufacturing, preserved knowledge libraries, and ways of renewing itself over and over again. The more seriously we imagine the journey, the less the craft resembles a single machine, and the more it resembles an artificial habitat. Even emotionally, the idea changes. A short mission can be driven by courage, focus, and the hope of return. A mission that becomes a world has to support ordinary life as well. People would still need meaning, belonging, beauty, rest, privacy, social order, and some sense that life is more than maintenance. Human beings do not live by oxygen and calories alone. A sealed civilization moving through interstellar darkness would need to carry enough humanity to remain human. That may be one of the hardest parts to picture, but it matters deeply. Because once the ship becomes a world, the engine is no longer the only heart of the mission. The people, the systems, and the continuity of life become the heart of it too. The challenge grows from engineering to ecology, from velocity to habitability, from survival to sustained existence. And once the spacecraft has changed in that way, another question rises almost on its own. If the ship becomes a world that lasts longer than ordinary lives, then who is really making the journey in the end? A journey across the galaxy is already difficult to imagine in terms of distance and speed. But when human lives are placed inside that journey, another truth begins to settle in. The people who choose to leave may never be the people who come closest to finishing. In many versions of the trip, they would not even live long enough to see more than the very beginning of it. That changes the emotional center of the mission. Most journeys in human history have carried a simple promise. The people who depart are the ones who hope to arrive. Even when travel is hard, even when the road is dangerous, the basic shape remains familiar. A person leaves one place and reaches another. But once the timeline stretches beyond ordinary life, that shape begins to dissolve. The mission continues, but the original travelers slowly become ancestors rather than passengers. This is where the idea of a generation ship begins to matter. A generation ship is a vessel designed not for one lifetime, but for many. The people on board would live, work, age, and die there. Their children would grow up there. Their grandchildren might never see Earth at all, except through stories, records, images, and inherited memory. In that sense, the mission becomes less like an expedition and more like a chain of human continuity moving through space. That is a very different kind of travel. The goal remains out ahead somewhere in theory, but daily life would no longer revolve around arrival in the way we usually imagine. Most people born aboard such a ship would not experience themselves as people on the way in a temporary sense. They would experience themselves as members of a society that happens to exist inside a moving structure. The journey would still define their world, but it would do so the way history defines ours. It would be the condition they inherit, not a dramatic departure they personally chose. That inheritance changes identity. The first generation might think of itself as leaving Earth. The next might think of itself as preserving a mission. A later generation might think of the ship itself as home and Earth as something legendary, emotionally powerful, but increasingly distant. Over enough time, even shared purpose would need maintenance. A society cannot remain stable for centuries or millennia, simply because the original launch felt meaningful. It would need education, culture, institutions, memory, and reasons renewed again and again. So time does more than lengthen the mission. It reshapes the people inside it. Even language could change. Beliefs could change. Priorities could change. Small design decisions made by the first builders might affect daily life for descendants far removed from the launch. A hallway, a food system, a schooling method, a social rule. Any of these could become part of a culture rather than merely part of an engineering plan. The ship would carry bodies through space, but it would also carry history, and history always changes the ones living inside it. This is why the mission grows stranger the longer we think about it. The question is no longer only whether human beings can build a powerful enough craft. It becomes whether human continuity itself can be sustained across spans of time that detach departure from arrival. The journey turns into a test of succession. Can one generation hand purpose, knowledge, and stability to the next without losing too much of what made the mission possible in the first place? Some people imagine non-traditional solutions here. Suspended animation, embryo-based settlement, artificial intelligence, or digital forms of continuity are often proposed as ways to reduce the burden of long-duration human travel. Each of those ideas changes the mission in major ways, and each brings its own ethical and technical problems. But even without choosing among them, one truth already stands clearly enough. A true galactic escape is larger than one lifetime. That may be the simplest way to say it. The mission would not merely outlast individual people. It could outlast whole generations of memory. It could turn the travelers into a lineage rather than a crew. And once that happens, the spacecraft is no longer just moving through the galaxy. It is carrying a changing human story with it, one that will not remain identical to the story that began on Earth. Time, in other words, is not just something the ship passes through. Time becomes one of the forces that remakes the travelers themselves. And if the people on board would change that much over the course of the journey, another question begins to press quietly at the edge of the story. Over spans like these, would the Milky Way itself still look the same? By this point, the journey has already grown beyond the scale of one human life. Now it begins to grow beyond the idea of a fixed galaxy as well. It is easy to picture the Milky Way as a still image. We see drawings of spiral arms, a bright center, a broad disk, and a faint outer halo. And the galaxy begins to feel like a giant map hanging in space. That picture is useful. It helps us understand shape. But it can also quietly mislead us, because the Milky Way is not standing still while we think about leaving it. Everything inside it is moving. The sun is moving. The stars around us are moving. The gas clouds in the disk are moving. Our whole solar system is orbiting the galactic center at tremendous speed, taking roughly 225 to 250 million years to complete one full circuit. That means even during the age of the dinosaurs, the sun was in a different part of its journey around the Milky Way than it is now. The night sky looked different then, and given enough time, it will look different again. That matters because a galactic escape mission lasting hundreds of thousands, millions, or even longer would not unfold against a frozen background. The galaxy itself would be changing the whole time. The spiral arms are a good example. They are often drawn as though they are solid, permanent lanes of stars, like glowing roads fixed in place. In reality, they are more like large patterns moving through the disk, shaped by density waves, star formation, and the motion of material through the galaxy. Stars move in and out of these larger patterns over time. So if a spacecraft were traveling outward over immense spans, the Milky Way it moved through would not remain exactly the Milky Way it first set out from. Even the stars closest to us would slowly shift. Constellations feel permanent because human lives are short. Orion, Scorpius, Ursa Major, and the others seem as though they belong to the sky itself. But over long enough periods, stars drift through space and their patterns distort. A ship, carrying generation after generation away from Earth, would not inherit the same sky forever. Familiar shapes would slowly loosen and change. The galaxy behind the travelers would remain recognizable for a long time, but the details would never be fully still. The center of the Milky Way would continue its own story too. Stars would keep orbiting there. Gas would keep flowing. New stars would form in some places, while older stars died in others. Supernovae would erupt. Clusters would move through the halo. The galaxy would continue behaving like a living system of motion, birth, loss, and rearrangement. It would not pause simply because a spacecraft had begun trying to leave it. And beyond the Milky Way, larger motions continue as well. Nearby galaxies are moving through space too. The Andromeda Galaxy, for example, is slowly approaching the Milky Way, and over billions of years, the two are expected to merge. That event belongs to a timescale far larger than any near-term mission, but it reminds us of something important. Galaxies are not permanent islands locked in identical poses forever. They evolve, interact, and change shape over deep time. So the target refuses to stay still. This is where the scale of the journey becomes more than human. Earlier, time stretched beyond a lifetime. Then it stretched beyond civilization. Now it begins to touch the level where even the larger cosmic setting is in motion. The ship is changing. The people aboard are changing. And the galaxy they are trying to leave is changing too. That has a strange effect on the meaning of escape. If the Milky Way is dynamic, then leaving it is not like heading toward the edge of a frozen object. It is more like moving outward from within a great rotating system that continues to reshape itself while you travel. The stars behind you shift. The patterns around you drift. The broader structure remains real, but it is never exactly the same from one age to the next. In a way, that makes the journey feel even lonelier. The travelers would not only be separating from home, they would be separating from a home that is itself evolving, becoming something slightly different with every passing era. What they remembered from the early days of the mission would slowly stop matching the galaxy around them. Even memory would begin to lag behind reality. And once that settles in, another question begins to rise naturally. If the galaxy changes while you are leaving it, then what would departure actually feel like from inside the ship? At a certain point, the numbers and definitions begin to give way to something more personal. What would it actually feel like to leave? Human beings are used to departures that announce themselves clearly. A shoreline falls behind. A mountain range fades in the distance. A city becomes a cluster of lights in the rear window. There is usually a moment when the mind can say with confidence that one place has ended and another has begun. The Milky Way may not offer that kind of moment. A traveler moving outward through the galaxy would not pass a bright line hanging in space. There would be no giant border, no final wall of stars, no sudden crossing where the ship emerges into a clean new realm. Departure would likely arrive slowly, almost quietly, through thinning, spacing, and change in perspective. At first, the sky around the ship would still feel full. The stars of the Milky Way would surround the travelers in every direction, though more densely in some regions than others. The broad galactic disk, the structure we now experience from inside, would still shape the view. There would still be a sense of living within a star-filled environment, inside a great system that stretches far beyond the ship's local world. But as the outward journey continued, that feeling would begin to shift. The denser concentration of stars in the plane of the galaxy would slowly become more one-sided. The Milky Way would begin to feel less like the setting around the travelers and more like a region lying behind them or below them, depending on the path taken. The familiar immersion would weaken. The galaxy would stop being the medium of life and start becoming an object with direction. That may be the first true emotional sign of departure. Home would no longer be everywhere. It would gather itself into a part of the sky. Over still greater distance, the bright disk would grow thinner and more contained. The thick cloud of background stars that once gave the sky its sense of fullness would begin to loosen. Darkness would open wider between visible structures. The Milky Way would remain present, but its presence would feel more limited, more distant, more like a destination already passed through than a place still inhabited. This would probably be a very slow change. One generation might barely notice it. The next might inherit old sky maps and compare them with what they actually see. Over long enough spans, people aboard the ship might grow up knowing the Milky Way as a great luminous shape in one part of the sky, rather than as the all-enclosing galactic environment their ancestors once moved through. The change would not need a dramatic moment to be real. It would become real by accumulating, year after year, until one day the older view felt almost impossible to imagine. That is what makes this kind of escape so unusual. It would be experienced less as crossing and more as separation. The galaxy would not disappear. It would shrink into form. Its scattered brightness would begin organizing itself into something the eye could hold more easily. The countless stars that once felt like the fabric of the night would start behaving more like the visible body of a distant system. The travelers would not simply be farther from home. They would be seeing home differently, and that difference would carry emotional weight. There is something profound about watching your environment become an object. It means that what once surrounded you now occupies only part of the world before your eyes. Earth looks different from orbit because it stops feeling like the ground beneath life and becomes a sphere hanging in darkness. The Milky Way would undergo a similar transformation, only on a much greater scale. It would move from being the setting of existence to being something seen from outside the old familiarity of it. For the people aboard the ship, that might be one of the deepest markers of the journey. Not a border crossed, but a relationship changed. They would not wake one morning to a trumpet-like announcement that they had left the galaxy behind. They would wake into a slowly altered sky, a sky with more emptiness ahead, a sky where the Milky Way had begun, little by little, to gather into shape. And once that shape becomes clear enough, another question naturally follows. What would our galaxy actually look like once we were truly outside it? Eventually, the slow change in the sky would lead to a new kind of view. For most of human history, the Milky Way has felt endless. Even after science explained what it is, that feeling never fully went away. We still look up from inside it. We still see it as a band, a field, a surrounding presence. It feels like the larger world itself, the deep setting in which everything else happens. From outside, that feeling would begin to collapse. The Milky Way would no longer appear as a glowing river stretched across the sky. It would gather into one shape. Its disk, its bright center, its broader spread of stars, all of it would begin to organize into something the eye could hold at once. Home would stop feeling like an environment and start looking like an object. That shift would be hard to absorb. A galaxy is so large from within that the mind naturally treats it as a kind of cosmic background, almost like weather or landscape. But once enough distance opens up, the Milky Way would reveal its true outline. The central bulge would appear brighter and thicker. The disk would extend outward in a flattened sweep. Dust lanes would cut across it in dark, subtle bands. The spiral arms, which are so difficult to see clearly from our own position inside them, might begin to suggest themselves more naturally from a proper outside angle. And with enough distance, the whole thing would shine as one system. It would still be vast beyond anything familiar, of course. Even from outside, the Milky Way would not look tiny in any everyday sense. It would remain immense, brilliant, and complex. But compared with the feeling of being inside it, something fundamental would change. The galaxy would become finite. It would have a shape, a direction, a body, and an extent. It would no longer feel like the whole stage of reality. That may be the deepest reversal in the entire journey. The place that once seemed too large to leave would now fit into view. Not all at once at first, and not perfectly, but enough to transform our relationship with it. The same galaxy that made our fastest spacecraft feel slow, that stretched travel times into deep time, that held the sun and every human life within its motion, would now hang in the darkness as a single luminous structure among others. And that is where home suddenly shrinks. Not because it becomes unimportant, but because perspective changes scale. Earth looks small from orbit, yet still contains every human story. The Milky Way from outside would carry a similar feeling on a grander level. It would look bounded and contained, while still holding everything our species has ever known. Every mountain, every ocean, every city, every language, every act of love or fear or discovery, all of it would still be inside that glowing shape. That thought would likely feel both beautiful and unsettling. Beautiful because it would finally let us see our galaxy whole, or at least more whole than any civilization born inside it ever naturally can. Unsettling because something that once felt endless would now reveal its edges. It would no longer stand in for the universe. It would become one member of the universe. And in that moment, the Milky Way would stop feeling like everything. It would become our galaxy rather than the galaxy, a home rather than the whole. The night beyond it would begin to matter in a different way. Once the mind accepts that the Milky Way has become an object in space, it immediately begins to wonder about the space around that object. What fills the darkness beyond it? How empty is it? Are there nearby structures, distant galaxies, drifting gas, or only vast stretches of separation? Once home has finally gathered into a visible form behind you, the emptiness ahead is no longer just abstract darkness. It becomes the next landscape. And that leads naturally to the next question. Once we are outside our galaxy, what are we actually traveling through? Once the Milky Way has gathered into a shape behind you, the darkness ahead begins to feel different. From inside a galaxy, empty space often seems like a gap between stars. From outside a galaxy, it becomes a region in its own right. It has its own scale, its own quiet, and its own strange kind of structure. Escaping the Milky Way does not place a traveler into simple nothingness. It places them into intergalactic space. And intergalactic space is sparse, cold, and immense in a way that makes even a galaxy begin to feel local. At first glance, it might seem almost empty. The stars that once filled the sky so densely would no longer surround the ship in the same way. The Milky Way would remain as a bright structure behind, but the space ahead would open into wider darkness. The nearest large galaxies would still be very far away. The Andromeda Galaxy, our closest large galactic neighbor, sits about 2.5 million light-years from us. That is a very different scale from the tens of thousands of light-years we have been dealing with inside the Milky Way. Leaving one galaxy does not bring the next one close. It only introduces a larger map. This is one of the great perspective shifts of the journey. Inside the Milky Way, the galaxy feels like the giant structure. Outside it, the galaxy becomes one object among many, separated from others by stretches of space so large that even galactic travel starts to look small by comparison. The ship would have escaped one system only to discover that the next stage of the universe is measured in even wider distances. And yet, intergalactic space is not a blank void. It contains thin gas, scattered particles, radiation, dark matter, and the larger gravitational structure of the cosmos. Galaxies are not placed randomly like isolated islands in a featureless sea. They gather into groups and clusters, and those clusters connect across larger cosmic patterns. On the broadest scales, the universe forms a kind of web, with galaxies tracing out filaments and denser regions while larger voids open between them. So beyond the Milky Way lies not pure nothing, but a bigger architecture. That idea matters because it changes the emotional texture of the scene. The darkness would still feel overwhelming. The sparsity would still be real. But the traveler would no longer be leaving order behind and entering emptiness. They would be moving from one level of structure into another. The Milky Way would be part of a larger arrangement, and that arrangement would stretch far beyond any ordinary sense of destination. The local neighborhood of our galaxy helps make this concrete. The Milky Way is part of a small collection of galaxies known as the local group. Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies all belong to this broader family. So escaping the Milky Way does not mean leaving all galactic company behind at once. It means leaving our home galaxy while still remaining inside a wider regional setting shaped by other galaxies and their shared gravity. That makes the universe beyond the Milky Way feel more real. It is not just blackness after the border. It is a larger environment with its own distances, its own relationships, and its own immense separations. The ship would move outward into a setting where galaxies are no longer the whole world, but pieces of a broader cosmic landscape. There is something humbling in that. A journey that once seemed almost impossibly grand begins to reveal itself as only one step outward through nested layers of scale. First, there was Earth, then the solar system, then the Milky Way. Now, outside the galaxy, another setting opens, and it carries its own vastness with it. The farther we travel, the more the universe keeps refusing to become simple. That does not make the Milky Way smaller in any absolute sense. It makes the universe larger in relationship to it. And once that larger setting becomes visible in the mind, another question begins to grow more naturally than before. If intergalactic space is this sparse, this immense, and this far removed from any ordinary human life, then why would a species like ours ever try to go there at all? By now, the problem has grown so large that a different kind of question begins to take over. At first, the journey was about distance. Then it became about speed, gravity, survival, time, and the slow fading of home into a single shape behind us. But once all of that is understood, the mind naturally turns in another direction. Why would any species choose this at all? Why would human beings try to leave something as vast as the Milky Way and move into a darkness even larger? That is where the story stops being only about physics. It becomes about motive. One answer is survival. Human beings have always lived with the quiet knowledge that no place lasts forever. On small scales, that truth is easy to see. Cities change, climates shift, empires fall. On larger scales, planets face risks too. Asteroid impacts, supervolcanoes, long-term climate instability, and the eventual brightening of the sun all remind us that Earth, however precious, is not a permanent shelter. Even the solar system has limits. If a civilization survives long enough, it may eventually feel pressure to spread outward simply because staying in one place forever is a fragile plan. Seen that way, the journey begins to look less like a strange act of ambition and more like an extension of a pattern life already knows. Living things spread. They occupy new spaces. They adapt, divide, and carry themselves outward when conditions allow. A civilization with enough skill might one day do the same on a cosmic scale. Not because leaving home is easy, but because remaining only in one home may not be wise forever. Another answer is curiosity. This may sound softer than survival, but it is one of the deepest forces in human history. People cross oceans before they know exactly what waits on the other side. They climb mountains, enter caves, map the poles, and build telescopes powerful enough to study light, that began its journey before human beings existed. Curiosity is not an extra feature added onto civilization after basic needs are met. It is one of the things that helps create civilization in the first place. It pushes us past the known edge of things. In that sense, leaving the Milky Way would be the most extreme form of a very old human impulse. It would be an attempt to see from the outside what could only be guessed from within. It would be the largest possible version of stepping beyond the familiar and asking what else is there. There is also legacy. Civilizations do not only try to survive, they try to matter. They build monuments, stories, libraries, scientific instruments, and ways of passing memory forward. A mission to leave the galaxy would carry an enormous symbolic weight. It would say that a species born on one small planet had learned enough, endured enough, and imagined far enough to push beyond the system that shaped its earliest history. Even if the practical rewards were uncertain, the act itself would carry meaning. It would be a statement about what the species believes it can become. And then there is expansion, which sits somewhere between survival and ambition. If a civilization grows, learns to manage energy on larger scales, and develops technologies that make deep space travel possible, then movement outward may eventually stop looking impossible and start looking natural. What feels absurd to one century can become ordinary to another if enough knowledge accumulates in between. A people living across many worlds might see galactic escape the way earlier humans saw crossing an ocean. Difficult, dangerous, and costly, yes, but still a real frontier. None of these motives stand alone. In reality, they would likely overlap. Fear and wonder often travel together. A civilization may seek safety while also seeking meaning. It may expand because it must and because it wants to. Human beings rarely move for only one reason, especially when the journey is large enough to define an age. That is why the question has changed again. We are no longer only asking whether the journey can be done. We are asking what kind of need, hope, or belief could be strong enough to justify it. Once that enters the frame, the mission becomes more human than ever. It stops being just a technical dream and becomes a mirror held up to our values. And that leads to one final uncertainty before the ending begins to gather. If the practical value remains distant and unclear, if the costs are enormous and the destination is so far removed from ordinary life, does the journey still matter anyway? At this stage, the journey begins to turn back toward us. The distances are still there. The speeds are still there. The Milky Way is still as vast as it was when we first tried to picture leaving it. But after walking through the problem carefully, something else starts to become clear. The value of the question was never only in producing a number. The value was also in what that number forced us to see. A question like this acts almost like a mirror. It begins as a travel problem, something that sounds technical and measurable. How far? How fast? How long? Those are real questions, and they matter. But the deeper we followed them, the more they began revealing things about human beings, as much as about galaxies. They showed us how quickly our everyday instincts break when placed beside cosmic scale. They showed us that our proudest machines, so powerful near Earth, become small almost immediately when measured against a galaxy. And they showed us something quieter too. Even when the numbers become overwhelming, the mind keeps reaching outward anyway. That is worth noticing. Human beings are small in one sense. We live brief lives on a small world orbiting an ordinary star. Our bodies are fragile. Our tools are young. Even our longest history is tiny compared with the age of the Milky Way. None of that changed during this journey. If anything, it became clearer. The galaxy did not shrink for us. The universe did not become gentler because we wanted it to. And yet, there is another side to that picture. A species that can ask a question like this seriously is already doing something remarkable. We are not only trapped inside our scale, we are able to think beyond it. We can take the place where we were born, trace its position inside a galaxy, estimate the forces shaping that galaxy, compare them with our technology, and then imagine what it would mean to leave. That does not make us large in a physical sense, but it does show a kind of reach that is hard to ignore. Our bodies remain local. Our thought does not. That is why the question carries meaning even before it carries practical value. It stretches the mind. It trains humility. It removes the comforting illusion that the universe is arranged around human convenience. But it also protects something important. It protects ambition from becoming too small. Once you have looked at the Milky Way this way, once you have seen how large the system around us truly is, ordinary limits begin to feel different. You start to understand both how little we have done and how extraordinary it is that we have done anything at all. That mixture matters. Too much pride, and the journey becomes fantasy. Too much defeat, and the journey becomes meaningless. The better response lies somewhere in between. We are small, but not trivial. We are limited, but not incapable of wonder. We are early, perhaps very early, in whatever larger story intelligence may have in the universe. Questions like this remind us of that balance. They also change how we think about home. At the beginning, the Milky Way felt like a destination to leave. Along the way, it became a structure, then a gravitational system, then a changing environment, then finally, an object hanging in space behind us. That shifting perspective matters because it teaches us that even the largest things in our lives can become understandable when seen from a wider frame. Home is still home. It is still precious, but it is no longer mistaken for the whole. And maybe that is part of the real gift here. The question does not only ask whether we can escape a galaxy, it asks whether we are willing to see ourselves clearly inside one. By the time that settles in, the original problem has changed shape. It is no longer only about a ship, or a timeline, or some distant future mission. It has become a way of measuring our relationship to scale, limitation, memory, ambition, and meaning itself. And that leaves one final thought waiting quietly at the end. After all of this, what was the original question really measuring in the first place? In the end, the question was never small. It sounded small for a moment. It sounded like the kind of thing that might lead to a surprising number, a dramatic comparison, and then a simple answer. How long would it take to get beyond the Milky Way? That feels, at first, like a problem waiting for enough math. And the math mattered. It gave us a real beginning. It showed us that with today's technology, the journey belongs to spans of time so large they push beyond ordinary human travel, beyond memory, beyond even the continuity of civilizations. That number was real, but it was never the whole answer. The deeper we followed it, the more it began to reveal what kind of world we actually live in. A world where a galaxy is not a picture in the sky, but a structured system with mass, motion, layers, and reach. A world where leaving does not simply mean going far away, but moving fast enough to break free. A world where our fastest spacecraft, so impressive near Earth, becomes small when placed beside the scale of the Milky Way. And a world where the journey grows so long and so demanding that it stops being just a problem of engineering and becomes a problem of inheritance, survival, memory, and meaning. So the true answer turned out to be two answers living together. The first is numerical. If we tried with the tools human beings actually have in 2026, escape would take an almost unimaginable amount of time. Long enough that the language of ordinary travel begins to fail. Long enough that generations, species, and even the galaxy itself begin to change while the journey is still unfolding. The second answer is harder to measure, but just as real. The question tells us what happens when human ambition touches cosmic scale. It shows us how quickly our instincts break when we leave the familiar world of roads, ships, and lifetimes behind. It reminds us that the universe is not built to fit comfortably inside our habits of thought. And yet, even when the answer becomes overwhelming, something in us continues leaning toward it. We still want to know. We still want to picture the journey. We still want to understand what lies beyond the edge of the familiar. That may be the most human part of all. We are a species born on a small planet, carried around an ordinary star, living inside one galaxy among many. In physical size, we are almost nothing against that background. But the ability to ask questions larger than our present power gives us a different kind of scale. We may not be able to leave the Milky Way in any meaningful practical sense today, or tomorrow, or for a very long time. But we can already see the shape of the problem. We can measure it, imagine it, and let it change the way we understand our place in the universe. And perhaps that is where the real journey happened. Not only in the imagined ship moving outward through the dark, but here, in the mind, as home became larger, then smaller, then clearer. As the Milky Way changed from a glowing band in the sky to a real structure around us. As distance became time, and time became inheritance, and inheritance became perspective. By the end, the galaxy did not shrink. We simply learned how large it had been all along. That is what the opening question was really measuring. It was measuring the distance between human intuition and cosmic reality. It was measuring how far ordinary language can carry us before wonder has to take over. And it was measuring something hopeful too. The fact that even when the answer humbles us, it does not silence us. We still keep looking outward. We still keep building. We still keep asking what lies farther on. So if we ever do leave the Milky Way, it may happen first in this quieter sense. First by seeing clearly what it is, where we are, and how vast the journey truly would be. And sometimes that kind of seeing is its own form of arrival.